Hello everyone, my name is Ebenezer Wadena, and I am a PhD candidate at the University of California, Riverside. Between October and this past February, I have been an intern for the Parallel Computing Lab at Intel under Dr. Hongbo Rong. In this presentation, I will discuss my work this past winter, embedding a domain-specific language in SYCL for productive and performant tensor computing on heterogeneous devices. This work was built on top of the foundation of Intel's T2s, temporal to spatial programming, a language and compilation framework to enable portable tensor computation performance between device accelerators. I will begin by discussing the current state of T2s and its compilation flow. The current T2s compilation begins with standard domain-specific T2s code. When compiling, T2s will create an intermediate representation. This will produce LLVM code, which is then compiled for the host to interact with device code. The final step is to convert the device code from the intermediate representation to OpenCL and compile it to the FPGA device. Our solution is to extend the current compilation framework of T2s to now produce SYCL standard code to be compiled by the Data Parallel C++ compiler. This enables engineers to extend the same tensor computations to multiple hardware platforms, including temporal and spatial architectures. For this work, we focus our efforts on FPGA alone, with future plans to incorporate both GPU and CPU implementations. Here we have an example of a simplified gem implementation that a developer would create. First, the developer will create a T2s specification, such as for a systolic array to execute gem on FPGA, outlined via the T2s spec start and T2s spec end pragma directives. A key part of the specification is the compile to WinAPI method within T2s language, which we will investigate later in this presentation. Second, developers will allocate and define argument parameters on the host side. And lastly, the developer will invoke the matrix multiply via the T2s submit pragma directive. Following this implementation slightly alters the original T2s compilation flow. First, developers will pass the preprocessed code to our source-to-source preprocessor for code translation built with Clang. This will in turn invoke the T2s compiler and replace the T2s specifications, producing SYCL code through a code generator, while leaving the surrounding code untouched. Finally, the developer can follow the standard DPC++ compilation flow, producing an executable binary to run on the target hardware. Next, we will investigate each aspect of the compilation flow and its produced code. Let us take this example shown on the left to invoke T2s spec for gem. The concept is to invoke a systolic array on the FPGA hardware. This involves passing input and output data from the host to device and from the device to the host. User-managed caches in DRAM and SRAM and other abstract memory. And finally, input loader, feeder, and output drainer, collector, and unloader channels. This systolic array and peripherals is described by the user using the T2s domain-specific language framework. Inside the T2s specifications, developers can define input types and dimensions, along with uniform recurrence equations found within the top rectangle here. These recurrence equations allow for the definition of space-time transformations, creating the framework for a systolic array. This definition of systolic array can be altered for GPU use as well as FPGA. This definition is visible inside the middle rectangle. In the bottom rectangle, a GPU SIMT parallelism is defined by outlining GPU blocks and threads. Finally, the T2s language provides the compile to WinAPI method to generate device kernels using Intel's OneAPI and SYCL language. As mentioned before, this work only encompasses FPGA. However, this implementation allows for easy extension to GPUs and CPUs as well. We will now investigate our new compile to OneAPI method. We created a OneAPI SYCL code generator within T2s, exposed by the compile to OneAPI method. This function takes several arguments: a set of input arguments, a string that will be the name of the device function as well as the generated file name, and lastly, a set of T2s targets. T2s targets will either be an Intel FPGA or Intel GPU to target a device. Again, this work only focuses on the implementation of FPGA code. We will look at the produced final code next. Here we have an example of pre-processed gem code that we have been observing. Once passed into the preprocessor, a new file is created with the run.cpp suffix, as we see in the next slide. In the produced run file, several changes can be noted. The first change are seen in lines 1 through 3. The preprocessor has included a SYCL-generated header file which defines the FPGA device kernel. Secondly, on lines 33 through 44, the preprocessor has wrapped the developer-defined memory with domain-specific class structures necessary to interact with the generated device kernels. Next, on lines 47 through 53, the preprocessor has defined the SYCL device selector used by SYCL queues within the device kernel as well. And lastly, on lines 57 through 63, the preprocessor has implemented the execution of the generated gem function, along with printing out device kernel execution times for the developer. Next, we will investigate the generated OneAPI SYCL code in 4 stages. First, generated code wrapper function. Second, how host and device kernels are defined. Third, how memory is managed between the host and device kernel. And lastly, how the generated code provides performance metrics. For the generated wrapper function, there are 2 key parameters. The first is the SYCL device selector, which specifies if we are running on a real FPGA hardware or utilizing an FPGA emulator. The second is T2s halide runtime buffer to wrap a host-side argument. This allows for the management of host and device memory. Next, examination of the kernel shows that it is a simple SYCL device queue. Each device queue is executed automatically after submitting a single task. Each device kernel queue event is stored and used later for performance metrics. Next, the generated code also managed memory between device and host. The developer is responsible for allocating the correct size host memory. The device memory is allocated through the SYCL malloc device method. If host allocation buffers are required, the generated code will use the standard malloc as necessary. Memory copies from host to device are executed before kernels are submitted, and memory copies from device to host are submitted after kernels have completed. Finally, the generated code returns a double representing the end-to-end execution of the device kernels, excluding memory transfers. This requires the storage of device queue events as mentioned before. Here, we see a full build of the final executable in all stages. Note that this video recording is sped up for the sake of time. We have tested our implementation for 3 tensor-intensive applications: general matrix multiply, 2D convolution, and capsule convolution. Our initial implementation was developed on the Intel Dev Cloud utilizing the Area A10 FPGA. Our initial synthesis shows strong hardware utilization for a small systolic array. In conclusion, this work is able to develop a code generator for a domain-specific language to utilize SYCL, implement a source-to-source code preprocessor, and deliver non-trivial performance for tensor computation on FPGAs. In future work, we plan to optimize this initial combination of T2s with SYCL to deliver better performance, as well as extend to other hardware and accelerators to truly make T2s hardware agnostic. Thank you for your time and for the hard work of those who have contributed to this project.